I'm Kei Kao from University of Science and Technology of China. Today, I'll discuss our paper, Cross-Scale Pansharpening via ScaleFormer and the PanScale benchmark. In this work, we focus on a practical but underexplored problem: how to make pansharpening models generalize from small training crops to large, real-world satellite images. Most existing pansharpening methods are trained and evaluated on fixed low-resolution crops. However, real satellite images are much larger. This creates a clear train-test scale gap. Direct inference causes rapidly increasing memory cost, especially for transformer-based models. Tiled inference can reduce memory, but often introduces visible blocking artifacts. More importantly, the image statistics at small training crops and large inference scenes are different, leading to scale-induced distribution shifts and degraded fusion quality. To systematically study this problem, we introduce PanScale, the first cross-scale pansharpening dataset with a corresponding benchmark. It contains 3 sub-datasets from Jilin, Landsat, and SkySat, covering diverse spatial resolutions and scene types. Unlike previous datasets, PanScale supports both reduced resolution and full resolution testing across multiple scales. This allows us to evaluate not only fusion accuracy, but also robustness and efficiency when input resolution increases. The key idea of ScaleFormer is simple. Instead of directly modeling larger images as larger 2D feature maps, we reformulate resolution changes as sequence length changes. Each local patch keeps a fixed spatial size, so its local statistics remain stable. When the input image becomes larger, only the number of patches, or the sequence length, increases. This allows the model to separately learn spatial structures within each patch and scale-aware dependencies across patches. ScaleFormer contains 3 main components. First, the scale-aware patchify module converts the PAN and LRMS inputs into fixed-size patch sequences. During training, we use bucket sampling to expose the model to different effective sequence lengths, improving robustness to unseen resolutions. Second, the single transformer modules decouple feature modeling into 2 parts. Spatial transformers capture local spatial structures inside each patch, while sequence transformers capture long-range dependencies across patches. Third, the cross-transformer modules perform PAN-MS interaction in both spatial and sequence dimensions, enabling effective fusion of spatial details and spectral information. Finally, we use rotary positional embedding in the sequence dimension to improve extrapolation to longer sequences at higher resolutions. We evaluate ScaleFormer on 3 PanScale sub-datasets, including Jilin, Landsat, and SkySat. The benchmark covers both reduced resolution and full resolution testing, with input scales ranging from small training-like crops to large higher-resolution scenes. We compare our method with classical methods, CNN-based methods, transformer-based methods, Mamba-based methods, and recent strong pansharpening baselines. The visual comparisons further confirm the advantage of ScaleFormer. Existing methods may introduce blurred textures, spectral distortion, or blocking artifacts. Our method produces sharper spatial details and more coherent spectral information. The error maps also show lower reconstruction errors in local regions, especially around fine structures. The quantitative results show that ScaleFormer achieves the best average performance across all 3 datasets. Compared with existing methods, our model consistently improves PSNR and SSIM while reducing spectral and global reconstruction errors. This demonstrates that ScaleFormer not only improves fusion quality, but also generalizes well across different satellite sources. Besides accuracy, efficiency is also critical for real-world large-scale remote sensing applications. The GFLOPs and memory curves show that ScaleFormer has more controllable computational growth as resolution increases. This makes it more practical for higher resolution inference without relying heavily on tiled processing. To conclude, we identify cross-scale generalization as a key challenge for real-world pansharpening. We introduce PanScale and PanScale Bench for systematic multi-scale evaluation. We further propose ScaleFormer, which treats resolution generalization as sequence length generalization, with scale-aware patchify, decoupled spatial sequence modeling, and ROAD. ScaleFormer achieves accurate, stable, and efficient fusion across scales. Thank you. Thanks for coming. If you have any questions or would like more information, please contact me.